So in chapter 7, we move into kind of what's very physics-like in our understanding of chemistry. And kind of as our summary sheet shows us, the chapter is called Quantum Theory and Atomic Structure. So we're really thinking about light and energy and particles and waves, and we use all of that to try to understand how electrons and atoms are arranged, and then we'll move on and understand how that relates to physical and chemical properties and reactivities of elements. And so in this chapter, we begin kind of with just thinking about light and the electromagnetic spectrum. And at the end of this study sheet here, I've got kind of a nice figure that reminds us that the electromagnetic spectrum represents all different possible wavelengths of energy that's all moving at the same speed. It's moving at the speed of light. And so again, there's a few equations that we can think about here relating the speed of light to the wavelength and frequency of energy. We can actually get the energy of a photon of that light by using Planck's constant and the frequency of that light. We can actually combine these two equations, and we can get actually that the energy is equal to hc over nu. So we can get a few equations here that we can use to think about light and the electromagnetic spectrum. And so we'll think about wavelength, frequency, amplitude, and so forth. So we'll have several things that we'll do with these problems that allow us to interconvert and think about these. Now beyond that, we apply this to atoms when we think about atomic spectra. And so the concept is that when atoms get excited, they either emit light of a fixed wavelength, or again, to excite them, they're going to absorb light of a fixed wavelength. And that allows us to jump up gaps. And so we can use this Rydberg equation, which is modified for the hydrogen atom, and we can actually quantify exactly how much energy that is. And then using an equation like this, we can relate that to the wavelength or frequency of light that will be present there. The rest of the chapter kind of deals with some more qualitative aspects. We kind of go into some history here, some scientific history to talk about wave-particle duality with matter and energy. I'm not going to really cover any problems dealing with that, but the last part kind of gets into what's called the quantum mechanical model of the atom. And that's really starting to think about energy levels that electrons are in, the shape of the orbitals that are in, and again, some definitions to think about are the difference between an orbit and an orbital. So an orbit is the path that an electron will take as it moves around the nucleus of an atom. So that's an orbit. But the orbital is a mathematical probability of looking at any given space and finding that electron. So if you kind of imagine a time-lapse movie of an electron as it moves around different orbits, you can imagine that that creates our orbital. Again, there wasn't a lot of meat to this chapter in terms of physical problems to work through. So kind of the last skill in terms of something to think about is why this is important. And it's important because electrons, again, determine shapes of molecules. And shapes of molecules, their structures are what affords them function. And that's going to set us up for the next, actually, 5 chapters. 4 chapters after this, but 5 chapters total kind of dealing with molecular shape. So in chapter 8, we'll kind of revisit electron configuration and think about how that applies to trends in the periodic table. In chapter 9, we revisit chemical bonding and thinking about things beyond kind of just simplistic ionic and covalent bonding and thinking about how bonding truly happens. And then in chapter 10 and 11, we think more about covalent compounds and think about the shapes of those molecules, as well as some more aspects of shape when we think about theories of covalent bonding. So kind of an introduction to this chapter, but again, this chapter is very physics-like in terms of a lot of the things that we'll see might remind you of some things we dealt with or you might have seen in a physics class. So this first problem, pretty straightforward, interconverting wavelength and frequency. So this is just kind of a simple story to introduce us with 3 kinds of waves from the electromagnetic spectrum. So a dental hygienist uses X-rays to take a series of dental radiographs while a patient listens to a radio station, and there's the wavelength of the radio station, looks out a window and sees the blue sky, wavelength of 473 nanometers. So all we have to do with this problem is think about calculating the frequency of the electromagnetic radiation from each source. And again, assuming that each radiation travels at the speed of light, which is c, and that's 3 × 10⁸ meters per second. So again, if we write down all the information that we know, we always like to do that and think about where we want to go. We can write down that we know that there's 3 kinds of electromagnetic radiation here. We've got X-rays. And the X-rays, again, are going to have a wavelength of 1 angstrom. And that's not a unit of measure that we've seen so far. So 1 angstrom is actually 10 to the minus 10th meters. So an angstrom is 10 nanometers. So 1 angstrom is 10 nanometers. We've got the radio that we're listening to, and the wavelength of that is 325 centimeters. And I always think it's interesting to think about radio waves, because this is actually something that we could think about. Like 325 centimeters, that's like over 3 meter sticks. That's how long a single wave is going through a crest and a trough of a radio signal. So kind of interesting to imagine those very long waves kind of moving through the atmosphere here. And again, looking at the blue of the sky is going to be 473 nanometers. So very different units here. We've got angstroms, centimeters, and nanometers. In terms of where we want to go, we'd like to know the frequency of this radiation. So we'd like to know nu, which is again frequency. Again, some equations that we can use. The speed of light is again proportional to the wavelength of light and the frequency. So the frequency, the speed of light is 3 times 10 to the 8th meters per second, and that's a constant. And what this sets us up and reminds us is that there's an inverse relationship between wavelength and frequency. So as we get to very long waves, that must mean their frequency is much less. And again, to imagine frequency, imagine if you're sitting at your desk here and you're watching waves go by. And these waves all go by at the same speed, but you're sitting there with a kind of clicker, counting how many times you see a wave go by. Well, if you have a wave like this radio wave that's over 3 meters long, but it's moving at the same speed as a very tiny X-ray that's only 10 nanometers, if you're lining up all these rays end to end and clicking how many times you see them pass by, the frequency that you're going to see X-rays pass by is much greater than radio waves. And that's consistent with, again, radio waves having a very large wavelength means they have to have a very small frequency. So those two are inversely related. So not only conceptually is that important to think about, but it allows us to think about interconverting them using this equation. All right, so kind of going through and calculating, and I'm going to do the same calculation for each of these. So again, X-rays, again, we want to solve for frequency. So we're going to take this equation, we're going to solve for frequency. So it's going to be the speed of light over the wavelength. The speed of light is 3 times 10 to the 8th meters per second. And just like we've always had to do, we need to make sure that we have the correct units of these species. So I can go ahead here and I can put 1 angstrom in, but then I have to do a little mini unit conversion down here to be able to convert this and say that 1 angstrom is 10 to the minus 10th meters, because I need meters to cancel here. Angstroms will cancel with my unit conversion, and I'm going to be left with units of frequency, which are reciprocal seconds. So for X-rays, it's going to be 3 times 10 to the 18th reciprocal centimeters, and not centimeters, reciprocal seconds. And the units of reciprocal seconds are also referred to as hertz, H-E-R-T-Z, which is abbreviated Hz. So we can see, as we predicted, when we have a very short wavelength, we have a large number of these waves that are going to march by our kind of counting point every second. So 3 times 10 to the 18th of these are going to march by every second that we're sitting here. Now, clearly we can't count that fast with our little counter, but that's consistent with what we might expect. So let's go through and think about calculating these other frequencies. All right, so let's go through for radio waves. Again, I'm going to use the same equation. Nu equals C over lambda. We've got 3 times 10 to the 8th meters per second. And again, now our wavelength here for a radio was given in centimeters. So I'm going to put my 325 centimeters in here. And again, 100 centimeters is 1 meter. So this will end up being 3.25 meters. But when we go through and figure out then what our frequency is here, we're going to have 9.23 times 10 to the 1st reciprocal seconds. So again, we're going to have a situation here where we've got a fairly small number here in terms of our frequency. And that's kind of what we'd expect. As we get very long waves, we're going to have a very small frequency. So large wavelength is small frequency. And let's go then for our blue sky. So with our blue sky, using the same equation, 3 times 10 to the 8th meters per second. And we can then take our 473 nanometers, and we know that 1 meter is 10 to the 9th nanometers, and we get 6.34 times 10 to the 14th reciprocal seconds. And again, you can write this as 6.34 times 10 to the 14th per second. You can also write this as 6.34 times 10 to the 14th hertz.